Hello and welcome to the lecture on bioeffects and safety. In the last lecture, we discussed about safety in ultrasound imaging. We discussed how ultrasound interacts with tissues, creating thermal and mechanical bioeffects. Now, luckily, the safety profile of ultrasound is excellent over the past 50 to 70 years, and that is because a vigilant research community has advocated prioritizing safety. A lot of basic research has been performed on cavitation and thermal effects, which has improved our understanding of these bioeffects. Now in this lecture, we will discuss about the output display standard. This standard provides users with a direct on-screen index related to thermal and mechanical bioeffects and improves the safety. So now here is the basic history of the development of these thermal and mechanical indices. Till the early 90s, only the acoustic outputs of ultrasound scanners were limited by regulation. Now this continues to date because FDA has regulated the output, the spatial peak temporal average intensity should be less than 720 milliwatt per centimeter square. Similarly for the eye, which is a sensitive organ with not a lot of heat diffusion, the ISPTA should be less than 50 milliwatt per centimeter square for the eye. Now these metrics are pretty useful. However, it is still important to understand the relationship between bioeffects and acoustic parameters. Now note that effects can be frequency dependent and they may also differ for the type of tissue in question. Therefore, just the intensity alone may not be a sufficient metric. So that is where the thermal index and mechanical index were devised for relating these parameters with the bioeffects. So thermal index and mechanical index are regulatory indicators that help predict the possibility of bioeffects in diagnostic ultrasound. And these together form the output display standard, which was developed by a committee of scientists in guidance from regulatory agencies in the late 90s. Now it's important to note that these are relative indices and not absolute parameters. But the advantage is that these indices are present on the screen while the ultrasound exam is being taken, and this allows comparison and recording even in the future. If it's found that some particular insonation led to a particular bioeffect, we would have a record of what was the thermal index and the cavitation index being used at that time. So let's discuss thermal index in some detail. So thermal index is a measure of the potential of tissue heating during ultrasound imaging. Now tissue heating can happen due to deposition of energy, and this can happen in two ways. So first of all, think about absorption. We discussed in the last lecture that ultrasound attenuates when it propagates through tissue, and a large majority of attenuation happens because of absorption of ultrasound. Now here we are assuming that the ultrasound that is absorbed is primarily converted to heat. Also, conduction due to heated transducer surfaces can cause tissue heating. For example, let us consider high intensity focused ultrasound, a therapy modality in which high intensity ultrasound is used to destroy tumors. Now in this high intensity focused ultrasound, the treatment duration can be fairly long, because of which the transducer heats up, and sometimes the patients who are getting treated can get surface burns because of direct conduction of heat from the transducer surface to tissue. So this tissue heating is also an important mechanism apart from absorption deep in the body. Now the type of tissue heating or the amount of tissue heating can vary on the type and the location of the tissue and the transducer being used. Now let us discuss the thermal index definition. So thermal index is defined as the ratio of the acoustic power produced by the ultrasound transducer, and by the way this is the time average acoustic power, to the power required to raise the temperature of tissue by 1 degree Celsius. So now these are the parameters W0 by W deg, and W0 is the average acoustic power of the transducer and W deg is the power required to raise the temperature of tissue by 1 degree Celsius. Now, how do we know the power required to raise the temperature of tissue by 1 degree Celsius? This is done using models of tissue heating, and these are also supported by experiments. So now this thermal index links temperature predicting algorithms to a measured acoustic output parameter W0. Right? Like I said, W naught is a system dependent parameter which can be calibrated by the manufacturer. You can calculate the time average acoustic power being produced by the transducer, and that is what is your W naught. But W deg varies based on the tissue of interest. So because this is dependent on the type of tissue, thermal index is defined separately for various categories of tissues. The main categories of tissue are soft tissue, bone, and bone at surface, which is relevant to the thermal index. So therefore, we have three thermal indices: TIS, or thermal index for soft tissue; TIB, thermal index for bone; and TIC, thermal index for cranium or bone at surface. So let's discuss now TI for soft tissue or TIS. Now for soft tissue, where do you expect the maximum temperature rise to happen? This usually happens near the surface of the transducer, because the heating by conduction becomes more important here. The soft tissue has relatively low absorption. Now the behavior and the degree of heating at the surface can vary based on the type of transducer in use, the F number of the transducer, the aperture size, geometry of the transducer, etc. For array transducers, the area of beam overlap usually has the highest temperature rise. So this is shown in this schematic. What we are doing is, we are firing a beam here, then we are shifting and firing the beam again, and shifting and firing the beam again, and here you see 4 beams with some overlap between them, or rather some overlap between consecutive beams. So what's interesting is, this area of overlap receives 2 beams rather than 1, therefore the highest amount of temperature rise can be expected in this area. There are also other ways of imaging. For example, in plane wave imaging, all the transducers are fired together. We will discuss more on this later, but when all the transducers are fired together, usually the maximum heating is on the surface of the transducer or the part of the skin which is in direct contact with the surface of the transducer. So just to summarize, for transducer arrays, the area of beam overlap will be the highest temperature rise area, and for imaging with no scanning, such as in plane wave imaging, the entire surface area of the transducer will be the hot spot where the maximum temperature rise can be expected. Now let us discuss the TI for bone, which is also known as TIB. So we know that bones are highly attenuating, and majority of this attenuation is contributed by absorption. Now these bones create strong hotspots for temperature rise, and when we look at similar configuration as the last slide, when you have bone in the imaging region of interest, in addition to this overlapping areas of the beam near the transducer surface, the maximum temperature elevation can be expected at the bone interface. Same trend is also observed for non-scanned transducers. So even if you are using plane wave, you would expect high heating near the surface, but if a bone is present, probably you would have more temperature rise at the bone tissue interface or bone soft tissue interface. Now let's discuss TI for bone at surface or TI for cranium, which is called TIC or abbreviated as TIC. Now if the bone interface is near the transducer surface, then the transducer bone interface becomes the area with the highest temperature rise. So this is quite intuitive. We discussed in the previous slide where the overlapping regions of the beam will have the highest temperature elevation hotspots. But now you also have a beam in close proximity with that area. So it is not at all surprising that this is the region where you will find the highest temperature rise. And the same trend applies even for non-scanned imaging transducers. Like for example, if you are doing plane wave imaging where all the transducers are firing together, still you would expect the highest temperature rise near this interface of the bone and the transducer. Now let us discuss the limitations of thermal index. The thermal index is quite useful, but it is not an absolute metric. The possibility of heat-based bioeffects depend on a variety of factors, and not all are covered by the thermal index. Because it's based on a simplified theoretical model, but nonetheless, this is a conservative theoretical model, which is good. Now this model, which is used for deriving the thermal index, assumes a steady state behavior. It does not capture dynamics of temperature elevation and decrease. It also considers a few standard tissue types such as bone, bone at interface, soft tissue, etc. But tissue types are very diverse in the body and very inhomogeneous. It does not consider that, and it applies a simplification, which is a limitation. Further, it has some consideration for perfusion, but not a very complex consideration, a very simplified consideration for perfusion, which is a limitation. And lastly, it assumes a uniform exposure of ultrasound in the tissue of interest. So any local hotspots are ignored. So after discussing the thermal index, let's move on to mechanical bioeffects, which can be regulated by the mechanical index. So MI is a regulatory index. It gives you a number below which inertial cavitation is unlikely to occur. And this mechanical index displays the probability of cavitation occurring in a medium, or rather it's related to the probability of cavitation occurring in a medium with a transducer of a specific frequency and given a specific pressure. So how did MI develop? Scientists observe cavitations using high amplitude sources such as lithotripters. There were also some experiments in cells and in lower organisms where cavitation induced bioeffects were observed, and some non-fatal hemorrhages were observed in some mice experiments. So all these events sensitized the scientists to the possibility of cavitation in the human body, and therefore a mechanical index was developed as a result of a collaborative endeavor between scientists and regulatory agencies. So now the nucleation of bubbles in tissue depends on the peak negative pressure. We discussed this in the last lecture, that bubbles can be nucleated during the low pressure phase or the rarefaction phase of the ultrasound, and then these bubbles interact with the incoming ultrasound beam to produce these bioeffects. Now inertial cavitation depends on the peak negative pressure and has a threshold behavior. Note that peak negative pressure is also known as peak rarefactional pressure, and so once you cross a certain threshold, you get this inertial cavitation. By threshold behavior, I mean that till a certain peak negative pressure is reached, you will have qualitative and quantitative differences in the cavitation behavior, but the moment you cross the threshold, you will get the strong inertial cavitation. Now, inertial cavitation occurs for a certain frequency after a certain peak negative pressure threshold is crossed. So keeping this intuition in mind and using theory of cavitation, Apfel and Holland wrote a seminal paper from which this mechanical index was derived. So mechanical index is calculated as the derated peak negative pressure, which is essentially the pressure in situ at the location of interest. I'll discuss what I mean by derating in the next slide, but this is a peak negative pressure in megapascal, and then in the denominator you have a square root of frequency in megahertz. Also, the mechanical index is made dimensionless by multiplying it with relevant units so that it just becomes a number without any dimensions. Now, why it's called mechanical index? It is called mechanical index because p square by f. So here we have p by square root of f, but it's just related to this. So p square by f is proportional to the mechanical work that is performed on a bubble during the negative phase of the acoustic cycle. So that is why it is related to the mechanical work, and thus the name mechanical index. Now let's discuss derating. So how do we know the acoustic pressure in situ? Typically it's very challenging to assess acoustic pressure in situ in vivo, and therefore these measurements are generally performed in a water tank in a calibration system, and then an approximate derating factor is applied. So if we can choose the attenuation coefficient as 0.3 dB per centimeter per megahertz, then based on this factor we can see how much the beam weakens because of this attenuation in the location relative to the pressure that is measured in water. So after this derating factor is applied, then we get a good approximation of the pressure in situ in vivo, and then we divide it by square root of frequency in megahertz. That gives us the mechanical index. Now let me discuss some assumptions in the derivation of the mechanical index. So like I said, Apfel and Holland contributed to the theory related to the development of the mechanical index, and it is also supported by some experimental measurements. But here are some assumptions. Firstly, all nuclei sizes are present. So typically we have cavitation nuclei which then cause bubble growth, and due to inertial cavitation these bubbles then collapse, which happens because of the inertia of the surrounding fluid, right? So bubbles first grow very sharply and then collapse even more sharply, and that is characteristic of inertial cavitation. So now the cavitation depends on the initial size of the nuclei that is present, and here, for being conservative, for taking all sorts of possibilities into account, we assume that all nuclei sizes are present. Next, this derivation is performed for short pulses such as those used in diagnosis. So as we discussed earlier, in diagnostic ultrasound, we would like to maximize the axial resolution, so we use damped transducers so that there is no ringing and we get a short spatial pulse length. So such short pulses are used in the derivation of the mechanical index. We are considering a duty cycle lower than 1%, so it is not going to be applicable to continuous wave insonation, for example. Now, when inertial cavitation happens, then the collapse temperature or the temperature reached inside the interior of the bubble after the sharp collapse is very high. And in this case, the assumption is that it is about 5000 Kelvin. This is a very reasonable assumption actually. Also, the bubble is assumed to grow isothermally, meaning that it is in equilibrium with the surrounding environment during its growth, and then there is a sudden adiabatic implosion when the bubble collapses because of the inertia of the surrounding fluid. Next, the fluid that is considered or the host fluid is incompressible, and water is incompressible largely, and the tissue can also be considered incompressible, which is because it is largely composed of water. Further, to simplify the model, gas diffusion is neglected over the time scale of the oscillations, which is also a fairly reasonable assumption. Lastly, this model assumes a leading rarefractional half cycle. Essentially, it assumes that the rarefractional part happens first during the pulse. Now let's discuss about the MI limits. So proper use of MI is necessary, and it requires some consideration of the clinical context. So for soft tissue, the mechanical index limit is 1.9. We should always be less than 1.9, and that would reduce the probability of having inertial cavitation. However, for some organs such as the eye, which is very sensitive, the MI limit is only 0.23. Similarly, lung has a lot of gaseous pockets and there is a high probability of inertial cavitation, much higher compared to soft tissue, where it is unclear whether there are nuclei of all sizes present. But lung has a large number of nuclei, so therefore the MI is less than 0.7 for lungs, and also the MI is typically less than 0.1 for contrast enhanced imaging. This is because higher MIs also lead to bubble disruption, and there is a possibility of bioeffects because these polydispersed microbubbles are present. Therefore, to be conservative, MI less than 0.1 is used. Now, note that MI was not designed to predict bioeffects from stable cavitation in the presence of contrast agent. So lately there has been some development. A new index was reported called the cavitation index by the Holland group, but it is yet to be adopted by regulatory agencies, but it's a very interesting work. Now also MI, although there is some correlation with bubble disruption, at higher MI you will get more bubble disruption, but it is not the appropriate metric to be used for contrast agent destruction. So some people have reported it, but it was not designed to indicate contrast agent destruction. So that should be kept in mind. Also, the mechanical index derivation assumes short pulses and low duty cycles, so it should not be applied for long pulses or continuous wave ultrasound insonation. And it should also not be applied for studies with low kilohertz frequencies. For example, I have seen reports which are performed with 40 kilohertz ultrasound or 100 kilohertz ultrasound, and the authors have claimed that their study is very safe because the MI was lower than 1.9. So note that MI was derived for megahertz ultrasound pulses, and the behavior may be qualitatively different at those kilohertz frequencies. So it is probably not appropriate to use MI for these low kilohertz frequencies. To summarize, today we discussed output display standards. We discussed how these standards allow the sonographer to employ ultrasound without risks or to minimize risks. And we discussed the thermal index, how it is formulated. We discussed its limitations. We discussed the theoretical basis of mechanical index. Although we didn't derive it, we also discussed how we can correctly use the mechanical index. So with this, I would like to conclude this lecture. See you in the next lecture. Thank you.